Okay, let's look at section 6.2, which is day 2 for us, growth and decay. So we're going to use exponential functions to model the growth and decay. And then I think probably day 3 we'll look at Newton's law of cooling. So growth and decay, this should be somewhat familiar to you from previous classes, maybe chemistry or biology, and previous math courses. But the approach we'll take in calculus is to be able to write the differential equation and then solve it and take it into applications. So anytime you encounter a situation where the rate of change of a quantity over time is proportional to the amount present. So we've got this rate of change of some quantity is proportional to the amount of that object that is present, we end up with an equation that looks like dy dt is equal to ky. And so I get this, I'm going to say where y is my quantity, okay? So the rate of change of some quantity I did with respect to time is equal to or is proportional to, we pick up that proportionality constant, and then it is proportional to the amount present, y. So we have some quantity y that was on hand. Exponential growth and decay, if y is a differentiable function of t such that y is greater than 0 and y prime is equal to ky for some constant k, then we can solve it and get this equation that says y equals c e to the kt, where c is some initial value of k and then of y, and k is the proportionality constant. Exponential growth we know will occur when k is greater than 0, and decay occurs when k is less than 0. We've been through this scenario where we have solved the dy dt is equal to k times y, and I think by now you probably can predict what is going to happen, but we're going to use separable differential equations to do this. And separating our variables, I need to divide by y to bring it over, so I'll have 1 over y dy is equal to k dt, and then we will integrate both sides of the equation, and this will give me natural log of y, absolute value y is equal to k t dt, if I integrate on the right. And I want to figure out just y, so I'm going to take and apply a base of e to each side. On the left side here, I come out with y, and I can drop my absolute values because on the right side I have a positive quantity. And if I integrate this, ooh, what am I writing here? That should have been a plus c, shouldn't it? I would have had the integral of k dt was k times t plus c. Now e raised to the k times t plus c gives me capital C e to the kt, where this capital C is some initial quantity. And remember that this is equivalent to saying e to the kt e to the c with a multiplication of those bases. When I have bases that are the same, I can add their exponents. So in this spot where we have differential equations, so we had dy dt, it's just kind of a repeat, is equal to k times y. The amount of change is proportional to the amount present, and that will always solve out into this format. Okay. How long will it take an investment to double if it is invested at 6% interest rate with continuously compounding interest? Well, in this case, we could say our initial quantity C, I don't have an initial quantity, do I? But I want to double. So you could create some initial quantity. Maybe I want to say I have $1 invested, and then I want to see how long it takes it to double, so then I'll come out with $2. So I would set this up and say I want to come out with $2 if I invest $1. E to the k, 6% is my k value. And remember, we want to put that in decimal form. So it's 0.06 t. and then go into solving divide by 1, we can apply a natural log to each side, and that will allow the 0.06 t to come down. Power in front of the log, natural log of e is 1, so I get 0.06 t. And solving for t, then we end up with the natural log of 2 divided by 0.06. And if I solve that, t is approximately 11.55 years. Now, you probably are familiar with the PERT formula from previous classes. Well, that is exactly, what we used. The PERT formula and our CE to the KT are really identical, just different letters used. The rule of 72 is kind of a cool thing to look at. It's really a simplified way to determine how long an investment will take to double. Given a fixed annual interest rate, you can take that interest rate and divide it into 72, and it'll give you a quick estimation of how many years it'll take to double. So it's kind of cool, very quick way to do it. If we solved this doubling formula, you'll see that natural log 2 is equal to r e to the rt, get it right here, and then I would have, you know what, I'm one step ahead of myself, that's why. 2 is equal to e to the rt. Now let's take a natural log of both sides. Natural log of 2 equals rt natural log e. Natural log of e is 1, and then we can see here that time is equal to the natural log of 2 divided by any rate. And if I look at the natural log of 2, I get 0.69314547, and that would be equal to r times t. So if I put this into percent form, move this over, it says, or move this by 2 so that we get a rate and increase it by 2, I would have about a 70, right? And 70 divided by some rate will be an approximation for the amount of time it'll take an object to double, because that was our circumstance that we started with. And 72, why use 72? Well, 72 is a number that a lot of things go into. It has a ton of factors. 1, 2, 3 goes into it, 4 goes into it, 6 goes into it, 12 goes into it, 9 goes into it, 8 goes into it. A lot of numbers go into it. So it's a fairly nice number to work with. All right, by US law, yogurt contains 100 million bacteria per gram. And that would be, if you wanted to label some yogurt as yogurt, you would need 100 million bacteria per gram. And here's the scenario. At noon, some sterilized milk is inoculated with a yogurt culture so that the milk contains 400 bacteria per gram. Suppose that the bacterial growth rate is proportional to the number of bacteria present. Well, that indicates right there that this is going to follow the laws of growth here, so that we know dy dt is equal to some k times y, the amount present. And then at 1 p.m. there are 1,600 bacteria per gram. At 7 p.m. how many bacteria are there per gram? And at what time does the culture really become yogurt that we can officially label it? Well, we just talked about this. The differential equation is going to be dy dt is equal to k times y. And we know, we could solve the equation, but we've done enough of these. We know this is how it turns out, that y is equal to. Now, if I want to start solving, I need to know what my initial amount was. So I think I'll go through and figure out all the numbers that they gave us. At noon, sterilized milk inoculated with the yogurt culture, it contains 400 bacteria per gram. So at time 0, we had 400 bacteria. And at 1 p.m., there were 1,600. So at time equal 1, we had y equals 1,600. At 7 p.m., we want to know how many were present. And then when does it officially become yogurt? So at what time does y reach, what was it, 100 million? We can answer all those questions. So our initial value, just looking over here where we started keeping track of things, c would equal 400. So that would give me the equation y equals 400 e to the kt. Now I can find my k by using another initial condition. Let's use it when time was 1 and y was 1,600. And plug those into our previous equation. 1,600 is equal to 400 e to the kt, so 1 times t. Divide by 400 and we will have 4 equals e to the k. Solve out for k and we'll have natural log is equal to natural log of e raised to the k, which will give us just k. Now that I know k and I know my c, we can rewrite this and have a lot of good stuff on our equation here. 400 e to the natural log 4 times t. That's a nice equation to work with. If I wanted to know how many bacteria were present at time 7, or 7 p.m., which would be t equals 7, I would just go y equals 400 e natural log of 4 times 7. And grab a calculator. I come out with 6,553,600 bacteria at 7 p.m. When will the yogurt legally be able to be labeled as yogurt? Well, what we're trying to find is time, and what I want to have present is 100 million bacteria. So we'll just kind of reverse our scenario. Let's set 100 million equal to 400 e to the natural log 4 and then times t. I'll put it in front and solve this out. So let's divide by 400, giving us 250,000 is equal to e to the natural log 4 times t. And natural log both sides so we can get that t lower down. So natural log of 250,000 is equal to natural log 4 times t. Divide by natural log 4. Natural log 250,000 divided by natural log 4 will equal our time. And it turns out that time is 8.966, and that would be in hours from noontime, right? So you know what? It's going to be approximately 9 p.m. Getting really close to that. Kind of a cool problem. Number 3, the number of radioactive atoms, Y remaining after 5 days in a sample of polonium-210 that start with an initial radioactive atoms is given by this equation, which is familiar. It does give us the K value, and notice it's negative, so I know immediately that I am in decay mode. Find the element's half-life. Element's half-life would say that my initial quantity maybe started at 2 and fell to 1 then. I could say 1 is equal to 2 e to the negative 0.005 t. You really could make up any number you wanted for your initial quantity. I could have said I started with 400. Well, then its half-life would say it would be down to 200 in a certain amount of time, its half-life time. So you can use whatever values you want. Just make sure they're half. So now let's find its half-life. Let's find out how much time it takes. So I'll initially divide by 2. I'd have 1/2 equals e to the negative 0.005 t. Let's natural log both sides. So natural log of 1/2 is equal to natural log of e to that power will be just the power then, 0.005 t, divide by the negative 0.005 t, and we end up with 138.629 years, which would be its half-life. Part B says a sample of polonium-210 is not useful for an experiment after 95% of the radioactive nuclei have disintegrated. For about how many days will the sample be of use? So after 95% of it's gone, it's no longer usable. That means basically that when I get down to not 50, but 5% of the material left, I should stop using it. 5% of the material left, stop using your polonium. I think then I would want to set this up that when I get down to 5 and I had started with 100, I want to find out the time that it took to do that. And that'll tell me how long the sample is useful. 0.0005, and then the time it takes for that to happen. And then it's just, going through and solving it out. I'd have 0.05 is equal to e to the negative 0.005 t. Let's get the variable t down to the lower. So we'll natural log both sides. And that will result in the power remaining here times t, 0.005 t. Divide by that 0.005, so I'll end up with natural log of 0.05 divided by negative 0.005. That'll give us the time, and the time that takes is 599.146 days. All right, that's all I have for you. We will pick up with Newton's Law of Cooling tomorrow. Homework, you should be able to do this homework, page 418 in those few problems. So have a good day.